Just jump off real quick. My name is Abeyta. My partner Benjamin decided to make a safety device that can be attached to a bicycle that would measure the distance between cars passing by in areas where bicycle lanes are either poorly built or there are none. And then we would catalog that data and use it to get bicycle advocacy groups to propose new infrastructure or redesigning infrastructure in areas that are dangerous to cyclists.
Yeah. Oh, can they hear me?
Yes, I can hear you.
Awesome. Yeah, my name is Benjamin. So this is like my first introduction to IoT, really any sort of IT work or coding for that matter. I knew looked at a little bit of Python before, so this has been a great learning experience. And with the project, I wanted something that would be both useful and adaptable that we could use for other things. With me, I'm an avid bicyclist, and I know lots of other people are. It's a way that we can be eco-friendly. It's a way that we can think about living in a city, right? With if we want to have dense urban populations, how do you move people? How do you be inclusive? And so with the project, how do we make bicycling more accessible for everyone, right? We want to make it safer and we want to make people feel safe. And so that is really the driving motive behind this project. Thanks, and so it's not just me that would be interested in this. There's several bicycle advocacy groups in New Mexico, right? Nationally, there's thousands of different bicycle advocacy groups, bike clubs. There is 65 American cities that have bike sharing companies operating within them. And then there's countless city and state transportation commissions that are also tasked with developing bicycle and just transportation infrastructure in general. And I'm sure every parent would be happy to have their kids a little bit safer when they're out riding their bike.
So yeah, I just wanted to jump in. The bicycle sharing thing, it's been over the past few years, it's been getting really big. And it went from, I think it was 40 some in 2017 up to the 65 we have now. So a lot more cities are getting involved in bicycle sharing. And the thing about New Mexico is we don't have a bicycle sharing program at all. And I think one of the reasons we don't is because our state is not friendly to bikes. As you can see, there's a little factoid up there that says we're ranked 44. And we don't actually have a lot of bike lanes in a lot of places in Albuquerque for sure. And that's mostly because I believe that the city is very spread out. But with the inclusion of bicycles, I feel that naturally we would have denser urban environments, like Benjamin was saying. We'd have more of a cohesive ecosystem where people could bike around, thereby saving themselves money and also protecting the environment. We'd have a lot of more greenery in our cities as well. So that's definitely something I believe that New Mexico can step up on.
Yeah, so the component list for our device, you can see it's a relatively cheap device. Probably the most expensive thing was the camera and then having to use 2 microprocessors. We were sort of limited on what we could choose from because this is what we were learning. If I was to do this again, right, the microprocessor, we would use one of the second gens where they had multiple serial ports. But nonetheless, right, you could see that this is a feasible project that was done on a shoestring budget. So the first device, right, so with this project, right, we needed to be able to have a way to sense when objects got too close to bicycles, right? So we chose the ultrasonic sensor. The ultrasonic sensor was relatively reliable, relatively easy to program. It was fun walking around, going and getting my coffee with the sensor and, like a ruler, trying to see how far away everything was as we walked around to make sure how accurate it was. The one thing that we had to think about was the placement of the sensor because some of the cars, the way that they were shaped would reflect the sensor in a way that it wouldn't get proper readings. So that led us to believe that having it lower where it would get sort of straighter parts of the body of cars as well as the wheels would allow for accurate readings. Yeah, and you could see, we wrote the code right there where you could see where it sends off the signal, it waits for it, there's a small delay, and then it's able to do the math, right, and decide and figure out how far everything is. The GPS was probably one of the more finicky parts of this device. The it wouldn't work inside the building. So when we were trying to program everything right, we had to keep on going outside, and then also powering the GPS module. The powering of it was finicky. It didn't want to run off of the standard 3.3 volts or the USB port on the microprocessor. It preferred to run off of the lithium ion battery port. Which was good because we wanted to run off a battery anyways, but having to troubleshoot the sort of power management of this device before we could even get it to work, before we could even, as we were trying to get the code to work, was fun. Yeah.
All right, so I'm going to jump in here on this part. One of the goals of the project was to eventually take the data and use it to map locations where we felt were less safe or where infrastructure could be built or renovated to make bicyclists safer. And as a demonstration, the data that we had pulled from our sensors, we actually saved it in a comma-separated value file, and we used that to upload it to Google Maps. And we made our own personal map, and the map could actually have pictures attached to it too to show potentially the vehicle or the location that you're in when the snapshot was taken. And the GPS is very accurate to within, well, 5 meters, but accurate enough to get to the location of where the vehicle passed too close or where the bicycle lanes were not safe enough. And so going forward, I think that definitely that would be our next step, would to make draw a lot more data into the map and use it to, like I had said earlier, propose all these different infrastructure renovations to bicycle advocacy groups to lobby for. And so saving the data, we had decided to use a micro SD card to save the data locally. And that was to make sure that we had definitely a hard way to save the data without using the cloud. Now, the cloud was something that we had thought about using as well, potentially sending the data using real-time tagging or real-time geolocation to a server, maybe like a personal database or something that you can set up to track all the incidences or the incidents that occur while the bike is riding around, or whichever device you're using on multiple bikes, that we can have the data within one easy to use location instead of having to strip all these SD cards out. But for the initial design, we decided to use the micro SD card reader. And with our project, we had 2 argons because we had 2 UART connections, and that's for serial in, serial out using like a 2 connector pin out. And they only had 1, as Benjamin was saying, on the argon that we had used. And so by the end of the project, our enclosure was stuffed with wires because we had to use 2 argons and tons of wires for the serial peripheral interface for this micro SD card, plus the 2 UART connections for both of the argons. So the data, as I said, was saved in a comma-separated value file. This made it easy to pull out the different data that we needed, such as when we time-stamped it, the latitude, the longitude, and the altitude, of course, for the geotagging. And then it also provides us with the distance in centimeters. So that way we can see how close they were to determine, you know, if is it a reoccurring thing? Is this car coming by all the time at this distance? Or is it maybe a reckless driver who's getting too close to a bicyclist? So with the data that we pulled, initially we saved it as one data set to an Excel file. And potentially going forward, try to combine data maybe by the day. But for now, we just wanted to make sure that we were getting the readings within the Excel file correctly. So the camera that we used was the UCAM3 developed by the 40 Systems. The library that was actually written for it was written for a different version of the particle. And that was a little difficult to use. I wasn't able to fully integrate the camera. That was definitely one of the more challenging aspects of the project. The camera utilizes inbuilt JPEG compression. And so instead of just a simple take a raw photo and send it on to your SD card, you would have to actually compress it and then gather the data together. And that's actually shown here in the code snippet, where you have to take the size of the image and then you stick it in a for loop, and the for loop takes all the data and concatenates it together. And then when it's together, you can actually utilize it to write to the SD card. My challenge that I had with it is that the file writing of the actual array of values in the image buffer, the image size, I wasn't able to get it to display a picture. And the the latest or the furthest I got with it was that it would actually show the file as having data in it. Like, let's say I had a 28 megabyte picture, it would tell me that it's 28 megabytes in the file, but it wasn't able to actually display the picture, show it as a recognizable JPEG. And so for the photos, such as the one that we have up here of the car and the license plate, I'd actually use the built-in web server that they make in the example on our Argon to take a picture using like a web interface. So that's definitely something going forward that I'd want to integrate and definitely get working. The UCAM is also versatile in that it can take pictures and videos. And I think that using videos would be best for this application. We actually, funny story, we ordered the lens before the camera. We thought the lens was the camera. We thought we were getting a great deal, $10 camera. We got a 115-degree field of view lens, but that was a blessing in disguise because it allowed us to get much better shots. And if anything, if the car is at kind of an odd angle, you definitely take a better picture because of the wide angle. So for the enclosure, I just stuck a brief video in here of the Fusion 360 model that myself and Benjamin had designed. The enclosure is pretty small. It's about 3 inches wide, 3 or 4 inches wide, and then 5 or 6 inches tall. And we wanted to make it so that way it would actually fit in the triangle portion of the supports for the bike. However, we were having trouble mounting it. What we had actually done is that there are, on the model, we had slits, and in the slits we were putting hose clamps, and hose clamps were used to connect it to the bicycle. The hose clamp design that we had, it worked for one side, but not as well for the other.
Yeah, let me add something on that. So with the design, right, so after putting everything together, I realized that we could have made it much smaller, right? With it being like a portable device, right? Like every time I went to go like rewire something, like there could have been a little bit, made it a little bit smaller. In the very end, we did use the hose clamps to connect it to the bicycle. I ended up using old tires, bicycle tires, right here, that I cut up to put on so that way it could hold on real tight, right? So that way it wouldn't move. One of the problems with like having anything on a moving device, right, is if it moves itself, right? Like how are we going to get accurate signals if it's like wiggling, right? And so luckily we were able to get it on nice and tight. The positioning of the device, originally I wanted to put it on the bottom of the seat stay, right there where it connects to like sort of the bottom bracket, right, for the chains. But as you could see in the photo, like your foot would have been triggering the sensors to go off all the time. So we ended up putting it up a little bit higher. And then I think I might put it, and I think that was like a good compromise right there. I'm not sure if I'd want to put it up too much higher, but right there it was able to clear my feet, clear everything, and have all the sensors and the cameras going correctly. Yeah.
So the design methodology that we used for the actual enclosure was we wanted to prototype quickly. So we decided to 3D print using the resin printer. And as you can see, we used draft for the enclosure. The actual enclosure, like I said, it's not too big, but Benjamin noticed that I think we could get a lot smaller, more portable, and I think that the design we have with the hose clamps right now is fine. Potentially something better, but we don't want anything that would make it, adhesive to the bike. We thought about welding it early on, but because you need access to the actual interior, the way that we had it set up was that we were able to pull it on and off the bike with ease, and the inside actually opens up kind of like a book because we use hinges on the backside. So it's very easy to take off and get inside if you need to replace one of the components or maybe change the sensors out. But right now, the way that's 3D printed, it utilizes 2 holes for the ultrasonic sensor and an angled hole for the camera. So future considerations for the project would be using potentially LEDs to show that the cyclist who's riding this bike, maybe it triggered, right? And obviously, I'm sure they're going to be aware if the car got too close to them, but just like a nice visual indicator to say, hey, it's working. An accelerometer would be definitely something that I think we were planning to include if we had more time. Kind of, Brian actually had this idea where he was going to put accelerometers on dump trucks, but something that we could use to measure or not necessarily measure, but see how rough the roads are, maybe if they need more paving, that sort of thing. There's just all information that we could get these groups who want to advocate for better infrastructure. And then buttons, just things that we can.
And then for the additional application, for the button specifically, right, I wanted to have a way to be able to turn it on and off, right, to be able to have it can turn on and off the other functions. I was able to upload everything to like Adafruit right, where we're able to upload the GPS coordinates. They have a mapping function and have a button so that way you could turn it on and off from an application on your phone. So that way, like when you're putting your bike away or taking it up, like it wouldn't be triggering like events, right? It wouldn't be taking photos and sending data being like, oh, there's a car too close, you know, there's something going on. And so I think that would be very important sort of moving forward. Additional applications with this. One of the reasons why I picked this project, I thought there were lots of other applications, right? Retrofitting factories, forklifts, government vehicles, anti-theft devices, even on farms, right? You could put it somewhere where you have a problem with like cows or something, like getting too close to your stuff. Anywhere where you need to monitor the distance and have like reliable information on like what's actually happening, and then be able to see that whenever it needs.
So for the design, I had mentioned earlier that we use 2 particle argons. In the schematic here, we actually have.
It's a little lowly.
I was talking through Benjamin's mic. I was muted. So I was saying that we had used 2 particle argons earlier. The particle argons were only used because we needed a separate connection for the UCAM and the HCSR04 sensor, the ultrasonic. And that's because they both use TXRX connections for their UART serial ports. And there's only one on the argon. What we had actually learned later on during the project, but decided to continue with our current path just as a proof of concept, was that for the newer argons, you can actually use a software serial command directly through the microprocessor to turn a digital input into another UART input. So it would be not a hardware input, but it would be a software input that would think it was a TXRX input. And that would have cut down on our space and definitely on the cost too, since you at the current moment have to buy 2 argons to run the project. The UCAM was the most expensive part of the project, and it came in a little late, unfortunately. So integrating it was kind of definitely a step back, because we had already gone pretty far at that point of how we wanted everything to look, how we wanted everything to fit together. And so when we got the camera, we had to go back and rethink all of it. But as far as the connections for all the components go, it's a little muddled here in the schematic. It's a little hard to read. I probably should have done what Miguel did and used the actual fritzing picture where you can actually see the parts, not just the schematic. But here you can see that the different things that go into the first argon. I'm using the SPI interfaces on the left-hand side. I'm using ground and the battery connection here because everything on this side uses the 3.3 volts. So I'm not using the actual V-bus. I use the V-bus on the other side, and that's because the UCAM requires 5 volts. Without 5 volts, it actually won't work at all. But there weren't too many components. Like I said, really the extra argon was the big one. And at this point, actually, we're at the end of our slides, but I think that Benjamin had wanted to demonstrate the actual Adafruit IO. Let me actually, Brian, can you make him a host?
I can indeed. Okay, he is a host.
Awesome. So you can see it going, or hey, let me see.
Yes, share the screen first.
Sorry, share screen.
And while you're doing that, I'm trying to get the picture of cows with proximity sensors out of my mind. So,
yeah. Well, you know, anywhere where you have anything that's going on. So you can see right here, this is our code. You can see it working right there at the very bottom that we have with the coordinates coming up, right? I can place my hand over it, right? You can see where it publishes the data. It publishes it to Adafruit, to our SD card, as well as telling us like how far away the incident was. Let me see. And then if we go to the Adafruit board, right? Now you can see where it pops up. It tells us our coordinates. It tells us how far away the event was, right? And then soon we'll be able to map it. I have the code almost ready. I didn't want to plug it in today and then not be able to demonstrate it, like mess it up at the very last minute, but it's almost ready to go. Awesome. Thank you, folks. And if you have any questions.
Lee, Benjamin, great job for
Awesome.
batting cleanup for us. We're at the end of the 2 hours, but hopefully folks can hang on just for a question or two. I really appreciate the employers hanging with us through all these presentations.
Just for a question, have you guys thought about doing a sensor array of acoustic sensors?
So for the project, initially we had just decided that we wanted to use the distance sensor. Actually, a pitched module earlier on was the LiDAR sensor, but that was a little expensive. As far as the acoustic sensor, I haven't really thought of any uses for the current goals of the project, but definitely adding more sensors is never a bad thing. More data for one thing, and you can, depending on who you are, what you're doing, you can manipulate that data any way you want. How are you thinking of using the acoustic sensors, Jason?
We actually have, we've invented a new headlight that has a sensor array in it that goes in front of a car that actually gives you real world positioning. And one of the things you said earlier on, and we learned this when we were detecting airplanes with sensors like that, is that if you hit a curved shiny body, you end up deflecting or reflecting your signal and you get a bad reading. And so using an array gives you all sorts of different sensors to try to get an accurate signal. So I just wondered if you had thought about doing that.
Yeah, that would have been something to do. So our project was actually a little bit on the expensive side because of the camera that we had chosen. We had wanted to do it pretty low cost. We wanted to make a module that, if it broke when you're riding your bicycle, it wasn't going to be a huge loss. But definitely if we had more money, if we had a product that was more rugged or something that was designed to maybe mount directly to the bike, like maybe welding it to it, like we sell smart bikes, that would be definitely something that I would consider using more sensors.
Great. That sounds really good. I look forward to talking with you guys hopefully next week sometime, and we can get some equipment in your hands and see what you can do with it.
That'd be great. Thanks.
Okay.